Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to talk about the four subspaces of the matrix A. And I have that written up here. And here's what they are. We're going to find them. Some of them we've already discovered. We've discovered the null space and the column space. We're going to add two more to this today. So let's take a look at the matrix A. And A, we're going to start with a matrix we've looked at before. It's 1, 1, 1, 2 for the first row. The second row will be 0, 1, 2, 3. And the third row will be 1, 2, 4, 5. Now, we're also going to, for reasons you'll see why, we're going to make the matrix of E as well in this problem. So here we go. Let's start off. Our first operation is going to be row 3, and we're going to subtract 1, row 1. So that's going to take us to, I'm going to fill this screen here with all of our matrix operations, and then we'll get down to the nitty-gritty below. So this is going to take us to the matrix of, the first row remains the same, 1, 1, 1, 2. The second row is the same, 0, 1, 2, 3. Now the third row becomes 1 minus 1. That was a 0 by design, because remember, we're getting zeros underneath our first pivot. Then we have a 2 minus 1, a 4 minus, oops, I mistake. That should have been a 3. There we go. That'll work much nicer. Okay. Yes, you can just change your problems to make them have to work much better for you at any given moment, as I just did. So we have 3 minus 1, that's a 2. 5 minus 2, that's a 3. You should have said something, and we wouldn't have made that mistake. All right, let's continue. Now we're going to take row 3, and we're going to subtract 1 row 2 from that. So that's going to give us this new matrix, where what we're doing is we're going to have row 3 will be a 0 row. So the first row is the same, 1, 1, 1, 2. The second row will be the same, 0, 1, 2, 3. The third row, 0, 0, 0, 0. We're almost done. Now, remember, we need to take this to R. This would be kind of a modified looking matrix U. It's in a moderately upper area, or upper triangular. So what we need, though, is we have to look back. We have to look back at all of our pivots. Notice that I have a pivot here in the second row, which means I need to have a 0 above and below. Well, I have the 0 below. Now I need the 0 above, and we're going to take care of that by taking a row 1, and we'll subtract 1 row 2. And write my resulting matrix. I'm going to bring it over to this other side. It will be 1, 1. Oops, goodness gracious. I got into the habit of just copying things. So I have 1, then I have 1 minus 1. That's going to be a 0. 1 minus 2, that's a minus 1. I have a 2 minus 3, that's a minus 1. Row 2 remains the same, and so does row 3. So let's copy those. 0, 1, 2, 3, and 0, 0, 0, 0. There we go. This is the matrix of R. Now, before we continue much further, what I'd like to do is I would like to find the matrix E. The matrix E encodes all of our row operations. Well, let's write this. We'll write them in reverse. Well, you know what? We'll remember what they were. So the first one was, as we did use, was E31. And then our next row operation was E32. And finally, our third row operation we said was E12. And remember, if as long as you follow this pattern where you first write the row you're working on, then you write the row that you're using to work on that, you'll always have the right order of your index for your L's. So let's write this. So I'm going to write this out. So E12, that means that in the 1, 2, row 1, column 2, so row 1, column 2, I'm going to have a minus 1, and then a 0. And then the rest of this just looks like the identity matrix. Okay. Now when I go to E32, that means that in the row 3, column 2 position, the row 3, column 2 position, I'll have a minus 1. So that's going to be a 1, 0, 0. So row 1 is unchanged. Row 2 is unchanged. But row 3, we're going to have a 3, 2. So 0, minus 1, 1. And then our third matrix says that in the 3, 1 position, we'll have a minus 1. So let's do that. So 1, 0, 0, 0, 1, 0, minus 1, 0, 1. There. Okay, and let's multiply these up. I'm going to start by my multiplication here. It doesn't matter. Matrix multiplication is associative. So I'm going to just copy my E1, 2. So I'm going to have a 1, minus 1, 0, 0, 1, 0, 0, 0, 1. All right, and let's multiply E32 and E31. So my first row says, if I look here, my first row is just a copy of the first row here. The second row is a copy of the second row. It's the third row that we're going to have to slow down on. You may be able to move right through that, but I'm going to have to be careful here. So my first two rows are just the first two rows of E31. So I have a 1, 0, 0, 0, 1, 0. And then now this says, what this says here is it says you're going to take and you're going to subtract the second row from the third row. So when I do that, I'm going to have a subtract. I'm going to have a from the third row. So I have 0, minus 1. Then I'm going to have another minus 1, and then I'm going to pick up a 1. It looks like. Okay. Yeah, I think that's right. And then let's move on. So now let's multiply these two. And what this says here is this says we're going to, this is the key here. Let's look at this. Notice that the second row stays the same. It's just a copy of the second row. The third row here says I just need a copy of the third row. But the first row up here, this says I'm going to take the first row and I'm going to subtract the second from it. And that will be my new first row. So let's do that. That's going to be a 1, minus 1, and then a 0. And then my other two rows from this matrix are just copied. 0, 1, 0. Minus 1, minus 1, 1. Okay. Now, how do you know that you got this correct? You should always keep in mind if you're that instead of shooting to the answers, what you want to do is say, how can I check my work? How do I know if this is correct? And the answer is just take E, multiply it by A, and what should you get? You should end up with R. So, you know what? For the sake of example, I should model my own behavior or my own request. 1, minus 1, 0. 0, 1, 0. Minus 1, minus 1, 1. Let's take that. That's my new E matrix. Let's multiply it by A. And A is 1, 1, 1, 2. 0, 1, 2, 3. 1, 2. Remember, this is a 3, not a 4, and a 5. All right. Well, what does this say? Now, if you struggle with doing row operations quickly, you know what? Just go back to the dot product. That's just the simplest way to do this and not make a mistake. So this says we're going to take, I'm going to apply row 1 right here. This is my row 1. Maybe I should get a brighter row 1. That's not very bright. How about this? Take row 1 and we're going to multiply it. We're going to go through each column. Okay, well, when we do that, here's what happens. So this says we're going to take row 1. We're going to go a 1, and then we're going to subtract the second row. So that's going to be a 1 minus 0 for 1. Then I'm going to have a 1 minus 1. That's 0. 1 minus 2, and a 2 minus 3, okay? And then look at this. Now this is definitely some different colored territory here. Let's take this pretty pink. This might be the same pretty pink. Let's take this pretty yellow. Yellow-green, I guess. So they look the same. Oh, that's terrible. 0, 1, 0. Notice this just says copy the second row. Now if you want to use the dot product, you can, but I'm just going to copy 0, 1, 2, 3. And then let's see if I can actually find a color that looks a little different as a highlighter. Maybe this blue would work. On the blue, we'll see. Now this one, this is a total dot product territory here. But we're going to subtract the first row, subtract the second row, add the third row. Here we go. Let's do that. So that's going to be a minus 1, 0, plus 1 for a 0. Then I'm going to take a minus 1, minus another 1, and add 2 for a 0. Then I'm going to have a minus 1. I'll do it this way. A minus 1. That's not a minus 1 there. I'm going to do it blue. We're going to take a, you probably know all this. I'm probably going too slow for you. So this is a minus 1, minus 2, plus a 3. Well, that's going to be a 0. And let's do it one more time. So now I'm going to have a minus 2, minus 3, plus 5, and that is 0. And look at what we did. E times A gave us R. And so do you need to look in the back? Check your answer. The answer is no. No, you just verified that your work is correct. That's what I would encourage you to do on a test. So you don't have to worry. You'll know if you got it right or not. And you can find your mistakes if something didn't work. So, but let's remember what the problem was about. What the problem was is I need this. I need R. Oh, actually, let's do it this way. I need R and I need A. So let me copy R. Here's my matrix R. And I'm going to put it right down there. And I need my matrix A. So let me copy A here. Let's put it right next to it. And let's make it a little smaller, maybe. Put it right there. Now that's kind of crooked, but it still reads the same. You probably don't care about these things, but I do. It's just my nature. All right, I think we're ready. So let's do this. Let's see what we've got. So let's start with things we know. First, what do we know? We know that the column space of A comes from pivots in R, the matrix R. Well, where are my pivots? And let's look at this. I have pivots in column 1 and column 2. I guess I should be consistent there, shouldn't I? So I should probably make this a column with a capital C. Let's fix that so it looks consistent. Column 1 and column 2. So what does that tell us? It tells us a few things. First off, it says that the rank of A, the number of pivots is 2. And it says this, since the pivots are in column 1 and column 2, that means I use column 1 of A and column 2 of A to find my basis for A. So notice this. So the basis for column space of A is column 1 and column 2 of A. So I'm going to write this. We could say that the column space of A is equal to the matrix or the vector 1, 0, 1. And the vector, this is the basis, 1, 1, 2. Now, here is an interesting note. Note this. Note that this does not equal the column space of R. We could look at that right now and see, we could see that those are different spaces. So the column, if you were to use the vectors, the first two columns, let's just highlight this. If you were to use these first two columns here for your basis for the column space, well, those are completely different vectors. Those would give you the XY plane in R3. Well, if you look at over here, these two vectors, these are a plane in R3, but they're not on the XY axis. And so because of that, those are different column spaces in R3. And that's the next thing I wanted to write, is that the column space of A is a plane. Let's write that. Is a plane, and where is it? It's in R3. Okay, that's the first one. Now, let's take a look at this. Let's look at another one that we've calculated before. And that is the, you know what? Let's add one. Let's do, we're going to change the order. Let's go this way. In the same way that we can find the column space of A, we can also find what's called the row space. Now we're going to find the row space of A. And the notation, now this is going to, you have to be careful. You could write it as R of A, and you have to be careful that you realize that this R and this R, those are not the same R's. Those are not equal. Or you could also write it as the row space of A. Well, that's just the column space of A transposed. Of A transposed. Well, the answer actually is already on the page. It's already on the page. Now, you should actually ask how. Notice this. Well, what we have is the rank of A is 2. Well, what does that mean? That means that we have 2. It also tells us that that's not how you spell we. It says that we have 2 independent rows. 2 independent rows. So the row space of A, what can we write? We can write that then that the row space of A is very simply, now this is the interesting part, that the row space of A, you could write this as the first row in the matrix R. That's going to be 1, 0, minus 1, minus 1. And then the second row is going to be 0, 1, 2, 3. And you can clearly see those are independent, and they're independent if you look up here, because you've got, oh, whoops, totally hit the wrong button there. You can see that they're independent because if we look right here, what do we have? Well, this is just the identity components, and so right away we know that those are going to be independent. There's no linear combination or multiple from one to the other. But there's something else. In the same way that we said, okay, well, my pivots are in row 1 and row 2, so I can use row 1 and row 2 of A transposed, So that would say this. So this, believe it or not, it's the same space. This is equal to, it's the same column space if we say, okay, my first pivot is in the first row. The first row of A is the vector 1, 1, 1, 2. And my second pivot is in the second row, so my next basis vector could be 0, 1, 2, 3. Now you might say that really this is again, I'm going to write it this way. This is the column space of A transposed. Well, let me show you another way to convince you about this. So let's write A transposed. Well, that's the matrix of 1, 1, 1, 2, 0, 1, 2, 3, 1, 2, 3, 5. Well, let's go about finding the column space of A transpose in the same way that we found the column space of A. In other words, just take this to the matrix R. Well, what do we get? Well, we're not going to get the same R, but let's see. I'm going to start out, and here's my row operations. I'm going to do all of these at once. I'm going to take row 2 and I'm subtract a row 1. I'm going to take a row 3 and subtract row 1. And let's take row 4, and this time we're going to subtract, looks like 2 row 1s, and let's see what we get. Well, my first row stays the same, 1, 0, 1. And then I'm going to have a 1 minus 1 for 0, 1, and then a 2 minus 1. And then I'm going to get a 1 minus 1, 2 minus 0, 3 minus 1. And my last row is going to be a 0, or 2 minus 2, a 3 minus 0, and a 5 minus 2 for 3. Well, one more step, and this is just going to be a 0 row. That's because these are just multiples of row 2. Well, look at this. Look at what we have. Now, this is the same conundrum that we saw earlier. This is a different R. I'll call it R prime. This R prime says that, look, my pivots are in column 1 and column 2. So column 1 and column 2 of A transpose are my independent columns. And so again, that would just take me right back up to here. There's one more way that you might view this. And if you wanted to see, you're like, okay, how do I know those are the same? Well, a simple check. Just take one of these column spaces. For example, take the column space of 1, 1, 1, 2, 0, 1, 2, 3. So this is my basis, and then multiply it by some vector. We'll put in some numbers here. And are these other basis vectors in there? They have to be. If they're not, then this would be a false statement that I've written up above. So let's just see. Is that possible? Well, notice this. If I take one of the first row and I subtract this, or one of the first columns, and I subtract the second column, I have it. So in other words, either basis works. They're in the same space. So let's write what else we have. We've also found that notice this, that the row space of A, which is the column space of A transpose, has rank 2, which is the same as the rank we had, and now here's the interesting part, and is, where is it? It's in R4. Okay, so we need to be aware of that. So the column space of A transpose is in a different place. It's in R4. The column space of A, we said, is in R3. Now, we're going to need my R and A again. So let me go, actually I'm just going to take a look at R. Let me grab this and let's go to a new place on our page. So let's put that right there. Okay, now here's what I want to do with this. Let's look at this. Let's find the null space of A. The null space of A. Well, the null space of A, we can just write it from our solution. We know this. We know that we have the null space of A. Notice this. I have 1, 2. I have 2 columns that don't have pivots. Those become my free variables. Those become my free variables. And if you remember how we solved this, well, we just said that x is equal to, and we said that x1, we're going to have an x2, x3, x4. Well, this is very simply x1. Remember, the null space is when this equals 0. Excuse me. So this just says that we're going to have a, when we subtract x3 and x4 to the other side, so we write this as x1 equals, those are going to become positive. So now I have an x3 plus an x4. And x2, well, that's going to become a minus 2x3 plus, minus 3x4. x3, well, that's just x3. And remember, there's 0 x4s. 0x3 plus 1x4. I'm sorry, I'm distracted. There's some kind of a siren and a bullhorn going on outside. I'm going to pause this. I'll be right back. Okay, it looks like it was just a test to the local emergency broadcasting system. Now, what do we have? Well, if I separate these out in terms of x3 and x4, I have x3 times, I have a 1 minus 2, 1, 0, plus I have an x4, times 1 minus 3, 0, 1. And these are my special solutions. This is x3s1 plus x4s2. Well, that's just it. We're done. Because notice this. We have this identity component even in our special solutions, so those are obviously independent. Well, that's it. So we can say that the null space of A is S1 and S2. Okay, but let's see a little bit more that we found. Notice this, that the rank of A, so the rank of A is 2, and then the dimension of the null space of A, well, it's the number of columns. Ours is 4, and subtract the rank, that's how we get that too. It's n. This is in general is n minus r. That's our rank. We have one more thing. This is a new one for us. And that is what we're going to do as our last step. Our last step is this. Is now we want the null, we want the null space of A transposed. Well, there is more than one way to do this. There's more than one way to do this. But I'm going to show you, you know how to do it. You set up A transpose equal to 0, row reduce it, find the special solution. But let's look at this for a moment. Notice this. So the null space of A transpose. Our rank is still A. I'm sorry, our rank is still 2. But notice this. We had M, the number of rows, we have 3 rows. But we have 3 rows. Not only that, we have one row of 0 in row 3. So what does that tell us? That means that row 3 is dependent. Row 3 is dependent. So that means that we're going to have a null space. And we see this, the dimension, so then the dimension of the null space of A transposed is equal to the number of rows, 3, minus the rank of the matrix. Or in general, we'd say it's M minus R. And in our case, it's 1. Well, so the question is what's the basis? What's the basis? Well, we've already found it. We already found it. Let me show you where it is. The basis, so we could say a null space for A transpose is equal to the vector of, it's right up above, not quite yet. Here it comes. It's right here. It's this third line in the matrix of E. Because what do we know? That just says that if you take minus row 1, minus row 2, add it to row 3, you get 0. That's what this result was right here. You get 0. So in other words, and we'll check this. So minus 1, 1. So I'm going to write that. I'm pretty confident of that answer, but now minus 1, 1. But I'd like to show you this, that is in fact the answer. So let's just check. So if I wrote A transpose, so I write 1, 1, 1, 2, 0, 1, 2, 3, 1, 2, 3, 5. And I multiplied it by minus 1, 1, you can see clearly that just gives you the 0 vector. And there it is. That is our basis for the null space of A transposed. Well, where is the null space of A transposed? Well, because this vector right here has 3 components, the null space of A transposed is in, we'd say, is in R3. And I forgot to write it, but let's look at this. The null space of A over here, the null space of A, well, those special solutions have 4 components. So that's in R4. That's in R4. Well, I want to come down and draw a picture that we see in our book, and a picture that's actually quite helpful. Here's how the picture looks. So hopefully you have all that information memorized. If not, don't worry, we're going to go back and pick up what we need. We're going to draw it like this. Doesn't really exactly matter. And draw these boxes. Like this. Maybe make a copy over here. Okay, we have 2 spaces here, don't we? We have 2 spaces. One of these is in R4. R3. I'm going to put R3 over here. This is the space R3. So that means that this is going to, on the left, this will represent the space of R4. Now, what do we know? What did we say? The column space of A. Well, the column space of A had, each vector had 3 components. So the column space of A, that's over here. Okay? Well, let's just look up above. Now, what about the row space of A, or in other words, the column space of A transposed? Well, those vectors have 4 components, so we kind of keep them matched up. So we put our row spaces with our column spaces and our null spaces with our null spaces. But remember that the row space, or the column space of A transposed, that's in R4. That's in R4. Now here's the part that I always find really interesting, and that is that the null space of A. We said we said right up here. There it is. It's on the page. We said that the null space of A is in R4. In other words, That's this bottom corner over here. So this is the null space of A. And that makes sense because we're in our in our null space. If we looked up here, we see that we had 4 components in our solutions. So let's come down here. The last space that we had was the null space of A transpose. And we said, well, that's in R3. That's in R3. So this is my null space of A transposed. Okay. Now, the null space of A transpose also has another interesting name. Sometimes it's called the left null space. Now, let's see why. Why is it called the left null space? And the reason is that, so let's take a look at this. If I have the matrix A transpose, and I want to multiply it by some vector x, and I want to find out where it equals 0. That's a reasonable problem. Well, what if I transpose both sides? Well, this is going to be A transpose times x. We're going to transpose that. And then we're going to take 0, and we're going to transpose that. Well, what happens? A couple things. We switch the order, so now I have x transposed, A transposed, transposed, but that's A. And the 0 vector now becomes a row vector. But look at this. Now our vector is on the left. And it's multiplying not A transpose, but A. So it's the left null space. We should put that, it's the left null space of A. But finding it using this format is a little bit more difficult. So we just use A transpose X to find it. But now that you can see, it's the same thing. Finally, in general. So let's do some in general. So we'll put them in here in yellow. So in general. Here we go. We have, in general, A is M by N. Let's write each of our spaces. Well, the spaces stay in the same places, but notice this. So the number of rows, this is R, the space Rm. This is where my column space lies. So my row space lies in Rn. Think of the number of components in the rows, so it's Rn. So the column space of A, the dimension of the column space of A, well, it's the number of pivots in A, so it's R. And that's also the same for the row space. It's the dimension of the column space of A transposed is R. In our previous example, let me put that in here. Our previous example, we had this as a dimension was 2, the number of pivots, and so is this dimension 2. And let's do the white, the specific, our example for the null space of A. The null space of A was the dimension, we said we took the number of columns, subtracted the number of pivots, that gave us our 2 special variables, or 2 special solutions. And for the transpose, we have the dimension. Well, it was equal to the number of rows, 3, minus the number of pivots, so that was 1. Well, let's write this in general now. What do we have? So in general, the dimension of the null space of A, the dimension of the null space of A is equal to N minus R. N minus R. And the dimension of the left null space, or the null space of A transposed, it is M. M, the number of rows, minus the rank. And this is our general picture about the way the spaces of A are created. I hope that helps. Thanks for watching.